Let us now develop the SPICE simulation model for a 3-phase full bridge rectifier capacitor filter. So first let me change this title. I will make it as a 3-phase full bridge rectifier capacitor filter and place it there. We will remove these. Now we have to add 3 sources. Let us redesign these parts. So let me take that out. Now let us copy, paste, because we need a third arm, and I will put that there. Now you need to expand this a bit more. Let me pull it down so that you can accommodate more space here to accommodate a 3-phase star connection. Then make these connections proper, complete it. Complete this. Let me center this. Yes. Now we can move this together. We will make duplicates. Copy, control paste, control paste. So we have 3 sources. Remove. You can rearrange them accordingly so that doesn't clutter up. You have to name them. Let's say we name them as VA, VB, VC, or VSA, VS, VVSC. So VB, VC, then rename these diodes 5 and 6. So you have to give unique names for the components, those that you have copied, and then make this one as sine 0, sine omega t, and this one 13.3 milliseconds and 6.66 milliseconds. So you will have that. You will have to duplicate these and connect. Control copy, control paste. Copy, control paste, control paste. So let us rearrange and connect this. So after rearranging and then properly connecting, the entire 3-phase circuit looks like this. So you have VA, VB, VC. These are phase voltages with respect to the neutral. VB with respect to the neutral, VC with respect to neutral. So the phase voltages are 325 volts peak. Okay, and they are all delayed 120 degrees apart. And you have LSA, LSB, LSC as the lumped non-ideality in the AC line. RSA, RSB, RSC are the surge limiting 0.5, 0.5, 0.5 ohms surge limiting resistors. Then this is another non-ideality. This is extra diode set that we have put here. These two are the same. Now we will simulate. I have observed the node points that I have labeled. This is node A, node B, node C, node N. So if I say VA comma N, it will be between these two. If I see VA comma B, it will be the line voltage between A and B. VB comma C would be the line voltage between B and C, C and A, so on. So between this and this, it is line voltage. This and this, it is line voltages. So what do you expect here? It is the peak value of the line voltage, which will be 560. The voltages VA, VB, VC are with respect to the neutral. So this node will be 325 volts peak, 325 volts peak, 325 volts peak, or 230 volt RMS. Now the line to line voltage is root 3 times, which will be 400 volts RMS, and root 2 of that, around 560 volts, will be the peak, and you will be expecting 560 volts approximately about in that range across the output. So now let us see how we go about simulating, and let us see the various waveforms. We'd like to see the current at this point, would like to see this voltage, like to see all these three voltages. So let us modify the rectifier.cir circuit so that automatically it calls ngSpice, runs, and then plots the first draft waveforms. So look at this. I have opened rectifier.cir. These are the standard tran statement, and I include the netlist statement. I have included between the dot control and dot end C the control statements to be operated within the ngSpice environment automatically. I am setting the background color as white and foreground as dark black. Then asking ngSpice to run the simulation on the netlist and plot VAB, that is the line voltage A to B, that is from here to here, plot BC, that is this to this, and C to A. And I would like to see the inductor current here so that I will get this branch current, and I also would like to see V0. So let us have a look at all these waveforms in ngSpice after the simulation has been concluded. So for that, let us open a terminal. So we have opened the terminal, and let us run this simulation. I'm calling run sim and rectifier. So if you do that, goes into ngSpice, runs the simulation, plots. Let me maximize that. So you see a whole lot of plots here. You see these are the line voltage. Red, this one where my cursor is traveling through, that is VA to B. Blue, that is VB to C, and this yellowish color will be C to A. Green is the current in the branch just before the capacitor. You see after one cycle steady state is reached. See that at every point where there is a ripple where the output conducts, you will see the conduction here. You see this drop here is due to the resistive surge limiting. Otherwise this surge would be very, very high. Surge limiting circuits are similar. Even in the case of three-phase, you can use the circuits that we discussed for surge inrush current limiting even here. So after the first cycle surge limiting, you see that it goes into the steady state. You will see that there are 1, 2, 3, 4, 5, 6 6 ripples in a fundamental cycle. So the ripple frequency is 6 times. And this is the output wave shape. If you would like to see what would be the inrush current limit when we remove, or when we reduce the surge limiting resistor value, then you will see that the inrush surge limit can go to very, very large current values. Let us have a look at that also. I will change these values to 0.1 ohms, almost no surge limiting resistor there. This 0.1 ohms would represent all the line resistances and no more. So let me save this and let us go to the command line called rectifier, run that, and you see the first cycle inrush current 2.6 kilo units, 2.6 kilo amps, and then immediately in the next cycle you see that it has achieved steady state. And observe the drop, because we have reduced RS, the surge limiting resistor, the drops are much lesser. If you want to zoom to any particular place, right click, drag that, and you could see the zoomed values at that point. So this way I will recommend that you try to study the three-phase circuit and the various waveforms, branch currents, and node voltage waveforms at various points to understand, gather more insight into this three-phase full bridge rectifier C filter circuit. Very, very similar to the single phase full bridge rectifier C filter circuit.